Hey, welcome to class meeting 10 of EECE574, the graduate level probability and random processes. There are a few announcements. First one is that the midterm exam is approaching because we have around 28 class meetings, and now we have reached 10th meeting. So after or around after 14th class meeting, we will have a midterm exam. Unlike the quiz, midterm exam will be taken in the evening, and you will be given a lot of hours and free access to any material except any assistance from human being, live or dead. Anyway, homework 8 is assigned, and last time I said the due is today, but due is actually Thursday this week. And there will be a homework 9 assigned soon on our post-tech LMS system. Handouts and annotated handouts are always available at the primary course webpage. And you know how to access, right? You go to the cisl.posttech.ac.kr, which is the my labs homepage, and then you go to teaching and you find the EECE574, and then you click schedule and download. There are links to the PDFs and annotated PDFs, and also YouTube links, so you can access the material. For the passwords, as always, for example, this one have password 6 in lowercase letters, and I believe these handouts are not password protected. However, this chapter 9, section 1 may have password 9 instead of 1. So if it does not, 9 does not work, try 1. And if it does not work either, then let me know, okay? So corrections, clarifications, I have not found anything from the last class meeting. Let's see the overview. We are covering chapter 9 of the main textbook by Populis. And even though I said chapter 9 of the main textbook, actually we use the secondary textbook by Peebles and follow the chapter 6 in this order, section 2, 5, 6, 7, and we are here right now. And I have found Peebles' ordering is not that logical, and also Populis' ordering of materials is not logical, so I tried to combine, but I also found that my ordering is not yet logical, so I don't know what to do. But anyway, we are here, okay? After we finish chapter 6 of Peebles, and then we go to chapter 7 of Populis. And then we go back to chapter 9 of Populis. And there are several materials, topics we haven't yet covered. And after covering that, we will move to other chapters. Review. We were studying complex random vector. And before we studied complex random variable. And today we will be seeing more about the proper complex Gaussian random vectors. And then we are going to study the complex random processes, especially with emphasis with some Gaussian, proper Gaussian random processes. And then we will see the definition of complex vector valued random process. Many of you already guess what it would be. And then I will very, very briefly mention widely linear processing, which is a little bit different from the popular linear processing of complex valued variables, vectors, processes, etc. And then we will study time average and ergodicity as stated here. Got it? And you may say that why this course is so slow, and you know, right? Even though the tempo is very slow, probably you will be inundated by a lot of new terms, definitions, and even homework problems. And you have found that even though it is slow, you are gaining solid foundation for the study of future research. Okay, preview. Proper complex Gaussian random vector, CDF of norm, Markham's Q function, generalized Markham's Q function, and related distribution called chi-square distribution. And you may have heard about chi-square distribution, and then you'll be interested in finding the relation between chi-square central or non-central with the Markham's Q function and generalized Markham's Q function. So let's take a look at the very, very old, probably more than 10 years old, handwritten handout of my old course. So last time, we were here. So we started from real Gaussian, right? Real Gaussian, one-dimensional. So we had this notation, X. And this is called, sometimes people read follows, sometimes just read as the LaTeX command says sim. I don't know how to read, but usually I say that X is a normal random variable with mean 0 and variance 1, or Gaussian standard. X is a standard Gaussian random variable. And here goes our definition of Q function. And you must remember this. Q function is the complementary CDF of what? Of the standard Gaussian random variable. So mean is 0, variance is 1, and then you compute the tail end probability. Usually when we say tail end, we mean right tail. Okay, so here is a right tail, here is a left tail, but you compute the right tail probability from some value X. Let's say the horizontal axis means Y. Okay, so this area is Q of X. So you can easily guess what if X tends to negative infinity, Q of X is 1, right? Since this is the area, so if you increase X, the area decreases monotonically, right? And as you expected, if you draw Q function, then where it is? Yeah, here it is. So this is the graph of the Q function. Since it is the density, Gaussian density is symmetrical with respect to the origin. So you have left the y-axis intercept 1/2, right? And you have point symmetry with respect to 0, 1/2. Got it? And sometimes we have interest in the slope of this Q function, and also the 2 times second order derivative of this. And also, as I emphasized, sometimes we plot this Q function, not linear axis, but log axis. And this plot in log plane is very interesting, because if you plot this right side only, because X negative cannot be drawn in log plane, right? So you draw, then you have a so-called waterfall curve. Means this function tends to 0 very, very fast. Super linear and any super polynomial. So any polynomial that will be drawn as a straight line. Here, polynomial means in the denominator, you have a polynomial of X. Numerator, you may say 1. Any polynomial, asymptotically, when log X increases, it appears to be a straight line. But this Q function is decreasing much faster than any 1/, polynomial of X. In that sense, this Q function tends to 0 very, very fast as X tends to infinity. Got it? Now, that is the definition of Q of X. and that is the graph of Q over X. So you always remember this figure, that is the graph of the PDF of a standard normal random variable, and also remember this one, the Q function, the graph of Q function. And if you have enough endurance to remember, also remember this curve. Now, as a review, let me relate this Q function with the CDF of a general real valued normal random variable with mean mu and variance sigma square. Since this density of X now is different from that one, but it has 1 over square root of 2 pi sigma square e to the negative x minus mu square divided by 2 sigma square. You can easily see that what? The standard normal and the general normal can be easily related like this. Let me see. Let's say this as y, okay? Then what? Y equals x minus mu divided by sigma. In this way, you can always standardize or sometimes normalize non-zero mean, non-unit variance Gaussian to a standard normal. By the way, this method or modified version is still used when you take the qualifying exam in our department. So what you do is that we have samples that are your scores in some specific subject, and then we subtract mean value. So here goes subtracting the mean value, and then we divide it by the standard deviation. Then you have a unit list quantity y. And if your distribution is following exactly a normal distribution, usually the mean of the unit list quantity is 0, right? And the variance is 1. So what do we do? And then we multiply, for example, 10, and we add, for example, 60. Then what happens? Let's say this is z. Then z is normal with what? Mean 60 and standard deviation 10, right? Or sometimes we multiply 20, then something like that. Then what happens? If you obtain the raw data score around 2 sigma from the mean, 2 standard deviation from the mean, then what? You get 2 times 20 plus 60, right? So you get around 100. Got it? If you are from negative 2 standard deviation from the mean, then what happens? You have around 20. Got it? That is a kind of very standardized way in calibrating or adjusting score. Actually, similar method, of course, much complicated or delicate method is employed by our government, actually Department of Education. So when they modify or they, modify the Korean SAT score for the college entrance exam, they employ something similar. Anyway, so given a non-standard normal but normal random variable, if you want to find the CDF of this random variable x evaluated at a, then alpha, then what do? We just use this is the CCDF. So again, we are interested in the right tail, right? Right tail as we see here, right? So this is the density with mean mu and standard deviation sigma. And we want to set some value alpha, for example, and then we want to compute this area. And this area is the same as what? You plug in alpha and subtract mu to centralize and then divide by sigma. Then you get the CCDF of this Gaussian random variable x. Got it? So what people have done is this. As you've heard of, this Q function does not have a closed form expression. No closed form expression. By the way, closed form expression is not a formal way to describe this situation, but many people use. No closed form means that no mathematical formula in terms only of elementary functions. But here is the trick. What are elementary functions? Q function itself is an elementary function. So it's complicated, but usually when people say a closed form, they have polynomials, rational functions, and sine and cosine functions, and of course exponential functions. Okay, and sometimes hyperbolic sine, cosine, but no integration. Got it? No integration. So this right-hand side cannot be written as some sigma something with finite term. Be careful. Sometimes we may have infinite terms. So we have series expression to equate an expression with no closed form. But that expression with infinite terms is not usually called a closed form. Got it? So no closed form expression exists for Q function, which means that no Gaussian random variable has a closed form expression for the CDF or CCDF. So what do we do? What do our ancestors have done? They tabulated. They tabulated, which means that tabulate means that make a table. So here, this is x, and this is Q of x. And what do? They have 0, 1, 2, and as far as they want to go. And fortunately, if we divide these intervals very fine enough, as you've seen in your high school math, even logarithmic function can be tabulated, right? You've seen so-called 상용 로그표, that is the table of logarithmic function with base 10. And you've seen how to approximate and how to linearly approximate or linearly interpolate the lines in between, something like that in your math test books, right? Similarly, people tabulated this Q of x. And now let me ask you a question. You don't have the CDF of a general Gaussian. What do? You standardize and then use this table. As I told you, any CCDF of a Gaussian random variable can be expressed in terms of the CCDF of the standard Gaussian. So we only need to tabulate standard Gaussian tail end probability. Got it? Yeah, that's the idea. And we also talked about the relation between error function and the Q function. And the error function has very simple integrand. It is motivated by what is the integration of e to the negative something squared. So no scale at all. Got it? And then they try to find the scaling coefficient that makes this entire integral when x tends to infinity equals 1. So I have drawn a figure I remember, if I remember. Then here goes y e to the negative y squared. And then we wanted to integrate this region, right? But we wanted to have the entire integration equals 1. So this can be written as 1 over pi negative x to x, delete negative y squared dy. So actually, we wanted to compute the area here. And then we have found that the scaling coefficient is 1 over square root of pi. Just for convenience, due to the symmetry, we change the integration interval from 0 to x and we multiply by 2. That's the error function. And from this figure, you can see that the Q function is directly related to the tail end probability. So it's related to the complementary CDF. But error function is related to the CDF. Got it? So people defined so-called complementary error function. And that is more closely related to the Q function. And you can easily, by using the change of variables, you can easily see that Q function is proportional to complementary. C means complementary. Complementary error function times evaluated at x over square root 2 and multiplied by 1/2. Got it? So we've seen kind of first order properties, the zeroth order properties. And we have the first order derivative. And of course, as you remember, Q function is what? Monotonically decreasing function. So as we've seen from high school math, the first order derivative as a function is always negative value. And second order derivative. So we know the Q function has this shape, right? It's what? It has point symmetry with respect to origin 0, 1/2. And it seems that in linear scale, it's concave and convex. And as you guess, x double prime of x evaluated x positive is positive. So it's convex. And here is concave. So you have this property. And as I also mentioned, I tried to use, when I was a graduate student or your position, I had a problem that required the first and second order derivative of Q of 1 over square root x. And actually, that very simple math gave me to publish my result in a very good journal, actually. So you try that, got it? It seems you are not interested, then I have a tool to do that, right? Put it in the midterm and prove something. No. Actually, that alone does not work. So let me just talk about what I did when I was a graduate student. So I used the Q of 1 over square root of x. And also I used, in my problem, x was positive, but it was not that small. So I tried to find the first and second order derivative, which gave me, okay, if x is in communications engineers term, if the bit energy per noise density is greater than, for example, 2 dB, then that function has very nice property. And then I also used a kind of extended version of a mean value theorem. As you remember, mean value theorem is what? You have an interval, which means that you have 2 points. And it says the existence. So the mean value theorem, you must remember, as an existence theorem. Given 2 points, there exists a point between these 2 points such that blah, blah, blah. And that blah, blah, blah is in terms of the first order derivative, right? In my case, I have 3 points given. And then I show the existence of 2 points in between this interval and that interval. And then I also use the first and second order derivative to prove something. And that was quite interesting. So while I was running numerical example, I have found something is there, but I could not prove that. And I noticed that if I can prove that result analytically, then this result can be a very good publishable material in a prestigious journal. So I spend a lot of time. So we are here. So of course, people try to find upper and lower bounds on Q function, because as I told you, Q function does not have a closed form, which means that it is very hard to integrate some function, including Q function. So integration of something in the integrand, you have Q function, then it's very hard. So they try to find some polynomials or non-integration, including functions like this. See that if we allow the exponential function as an elementary function, then this lower and upper bound on some reason, okay, it does not always bounding, but on some reason, Q function is bounded by these 2 functions, and then you can handle. For example, here, as you see, this is in the logarithmic scale, and here, be careful, the horizontal axis is in a linear scale. So whenever you see Q of something, be careful. Got it? You have to check whether it is linear, or linear log, or log linear, something like that. Got it? And anyway, as the Wozencraft and Jacobs wanted to show the inequality, so here goes Q of alpha. So this is the line. And then he showed one very loose upper bound that is very, very well known. And we will be seeing how to derive this upper bound. And this says it's not tight. Here also, there is a term, an upper bound is tight. What does that mean? Usually, when we talk about an upper bound on a function, so we have f of x, and here is g sub n of x, parameterized by n. N is usually natural number. And if you increase n, or if you don't have parameter, in that case, usually you increase the argument. So in this case, you have, for example, for all x positive, you have this inequality. And then here, this inequality may not mean much because, for example, this function is in between 0 and 1, and this function is always greater than trillion, 1 trillion. Still, that is true, but it's usually upper bound, right? When we say this upper bound is a tight upper bound on this function, usually we mean asymptotically tight, means when x tends to infinity, this difference becomes very small. So here, as you see, this Q function and this upper bound is not tight, okay? And in that case, the antonym of tight is loose, okay? It's a loose upper bound. This is a loose upper bound on Q function. However, this function, no integration involved, is very tight. But we have to prove asymptotically equivalent or not in mathematically. But anyway, this curve, it was at that time very hard to even generate this plot, right? You know, people used Fortran to program it using punch card, and you have a syntax error. All your time, for example, 3 days, spent on borrowing a valuable CPU time in your central computing center is wasted, right? And now this is very easy. Just 3 or 4 lines in MATLAB, you can plot this. Anyway, if you plot this, even though you do not mathematically prove that bound is whether tight, asymptotically tight or not, this is practically tight enough, right? And also the lower bound, you see, here around at alpha equals 1 is very loose, right? Be careful. This lower bound is very loose when alpha is close to 1. However, if alpha becomes larger and larger, slightly larger than 2 or 3, then the lower bound is also tight enough for engineering application. I'm not claiming, and I do not remember whether these 2 bounds are really tight, but it seems that's correct. Anyway. So what you need to remember is that sometimes you may need some upper and lower bounds to handle in your problem. Then remember this figure, okay? Also, people have tried a lot of different approaches. And where it is? Yeah, there is also an approach using series expression. And here goes the well-known, famous approach, and saying that complementary error function can be represented by a Taylor series in terms of the Hermite polynomial of degree k-1 as, then you have this. Got it? So the case order derivative is given by this Hermite polynomial, and then what? Q function or complementary error function can be written as a Taylor series. And you cut at some very high degree polynomial or high degree. Got it? Let's go back to this one. So I've just shown you this is a loose upper bound, but very convenient. And we've seen here the loose upper bound. Got it? Then how can we derive this loose upper bound? There are many ways to derive, but I will give you one approach to show that. By the way, you've seen this upper bound. It's twice loose than the lower one, appearing in many undergraduate and graduate textbooks. And how do you do that? Probably you remember whenever you are hearing about tail end probability, probably your neurons say that pop, 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 and first Markov inequality, Chebyshev inequality, Chernoff inequality, blah, 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 right? And sometimes Jensen's inequality comes together. And by using one of the inequalities, the Chernoff inequality, or by using the Chernoff inequality, you find the bound, and you have a Chernoff bound. And this is the Chernoff bound on the Q function when the argument is non-negative. And this is not that difficult. And since I am assuming that you've taken undergraduate level probability and statistics or probability and random processes, I expect you do this yourself. Okay, so derive this inequality by using Chernoff bounding technique or Chernoff inequality. Now, let's derive the slightly tighter upper bound on Q of X. By the way, how can you find this? Anybody? There are many ways, but the simplest one is this one. As this hint provides, what you do is this. Consider X, that is 0 mean unit variance Gaussian, and also consider, let's say, Y, that is also standard Gaussian, and they are independent. Then, let's say this is X and that is Y. And you consider joint density of X and Y. Now, here is your Z-axis, and you can see the circularly symmetric Gaussian density, right? You see, I really want the VR device. But anyway, now I will find some value alpha here, and I will cut and shade this right half plane. And let me call this area as gamma. Then my question is this. What is the integration of this joint density of IID zero mean unit variance Gaussian on this area gamma? What is that? And you can easily rewrite this one as what? Y ranges from entire line and X ranges from alpha to infinity. Then, due to the independence of an X and Y, this integration becomes what? You can factor for X and for Y. And the first factor is 1, and the second factor is simply the right tail probability of standard Gaussian. So this is the interesting observation. So that in order to find the tail end probability of a one-dimensional Gaussian, it's very hard. So you consider this is a part of two-dimensional objects something. So what you think is an IID Gaussian, then what? You have contour of this joint density, and then consider that area for the integration. Then you have what? Q function. So here you have a Gaussian density that is circularly symmetric with respect to origin. You slice, as you slice your birthday cake, and then you eat every cake, and then what? That volume is Q of X. Got it? Now, anybody who try to find this inequality from that idea. So if you really want to work on yourself, by yourself, then you can work out today's class meeting room, and I will not say you are absent, okay? So I will give you 5 seconds to think. 4, 3, 2, 1, time's up. So the idea is this, very simple actually. Instead of integrating on this half plane, you cut this way. And then this shaded area is called gamma prime. Then what happens? You have this relation between two sets, the integration area gamma and gamma prime. And from the axiom of probability, what happens? Probability, which means the integration of the joint density on gamma prime is always greater than or equal to what? The integration of the joint density on gamma, which is Q of X. Okay? So you have this inequality. And interesting thing is what? Due to the symmetry, integration on gamma prime is what? Twice is twice the integration of gamma prime and what? How do I say that? Gamma double prime. And gamma double prime is that area. Okay? So as you see, due to the circular symmetry, this area, gamma prime, and the area outside the circle with radius alpha is what? When you integrate over gamma double prime, you get twice the integral on gamma prime. Okay? So which means that you integrate over gamma double prime and divide by 2, you have what? You have an upper bound on the Gaussian density. And this is now very easy to compute by using the conversion to polar coordinate. And as you've seen in the quiz 1, it's very easy. You can just integrate the Rayleigh distribution, or as you will see today, we integrate the exponential function and we get what? Something like this. Be careful here, x is non-negative. Ready? So this is the idea on how to derive this very simple bound. Got it? And by the way, this bound, heightened as this one, is used again and again and again and again, especially when we talk about some asymptotic property of a code. Okay, so when we want to know the high SNR property of a code, then we try to find the pair of code words that provides the minimum distance, and then plug in here, and then we discuss some results. Okay. Okay, got it. And here goes a very interesting expression of an alternate integration form of Q function. And this result was very, very recent with respect to me. Very recently introduced to Communications Society. However, the paper who introduced this formula to the Communications Society said that mathematician discovered that long ago, and it was not much used, but it was probably around mid-1990s, or even when I was a graduate student. So it was a very new paper and showed that Q of x can be written as this integral. And when I first saw the expression, I had no idea what does that mean. Anybody? So as usually I do, even today, when I saw the paper, I tried to derive that result myself without reading the paper, without reading any hint in appendix of the paper, and I failed. And it was very, very frustrating experience. And so after a few days, probably, I started to read. And interestingly, the method to proving this equality, this expression, is very similar to that idea. But no bounding. The idea is very simple. So as I told you, the Q function is the integration of the zero mean covariance identity matrix, Gaussian, right? Integrated on this gamma, on this area. And if you use the Cartesian coordinate to integrate this function on this interval, you immediately get x of x, q of x, right? What if you use polar coordinate without bounding? See that? This technique is actually using polar coordinate integration. But in order to apply that easily, we have to introduce gamma double prime, which eventually give us an upper bound, right? However, what if we still use polar coordinate to integrate that one, but we want to keep the equality? What do we do? And also, if you want to work out, you can work out. I'll give you 5 seconds. Okay, 4, 3, 2, 1. Okay, I will give you the idea. So I really hate this mass production of education. I want to teach just a single person and say that, okay, do you want any, how many hours? 2 days, okay? Then I will teach you other topic. Okay, let's go to the river and I will teach you how to row your boat, something like that. But unfortunately, we are not living in that area, in that period. So, so-called injectional method in Korean, right? 주입식 education. 주입식 교육, injectional education. I really hate, but this is the idea. So let me skip. Yeah, this is the idea. Here, just we rotated the integration reason, but result is the same. Okay, so this is 0, alpha, and our that area gamma is now here, just for convenience. Okay, because we want to set theta from 0 to pi. Got it? So before, our integration area on the right-hand half plane, but now it's kind of upper half plane. But the distance from origin is same, alpha. Got it? So what's going on? So if we apply the integration over this gamma, then we have q of alpha, right? And now we use polar coordinate integration. In order to do that, just take a point on this integration region. Let's say this point. Now this point has what? Distance from the origin and the angle from the x-axis, right? And let's say that distance as r and this angle as theta. Then how can we describe this gamma? As what? Some set of points in terms of r and theta. And you may say that it's a stupid idea, because if we use Cartesian coordinate, they are what? Separable, because density of an x and y are independent. However, we also know that from the quiz problem, and you know now, you now understand why I put that problem. R and theta is also what? Independent. If you have zero mean Gaussian, right? Actually, we are going to use that, even though we have slight difficulty. Now, write down this, the set of R of theta such that blah, blah, blah. So what is the part of blah, blah, blah? Anybody? So let's choose theta first. Got it? So when you are given theta, and this is alpha, r is what? Given theta, r must be greater than or equal to what? So sine theta equals what? Distance, right? Distance let's say this is distance, okay? Distance divided by alpha, right? So r must be greater than the distance, and distance is alpha sine theta. Is it correct? Something's wrong. Oh, okay, reversed. Yeah, I'm getting older. Okay, so right. So what is d? Got it? So you have theta from what? 0 to pi, right? And if you want, let's remove the endpoints. And given theta, what? R is greater than or equal to alpha divided by sine theta. And then what? You know, as you've seen in the quiz problem, you have r cosine theta, r sine theta, r dr d theta. And r ranges from alpha divided by sine theta to infinity. And theta ranges from 0 to pi. And you also easily notice that you can reduce the integration interval of for theta into 0 to pi, and then put 2 here. So 2 times 0 to pi over 2. Alpha divided by sine theta to infinity, blah, 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 dr d theta. And as we already know, the density, right, becomes what? 1 over 2 pi, and we have what? R e to the something, right? Something like this. So we just simply plug in, and then we have this expression. Got it? And now we've got the equality. We should not stop here. We have to what? Visualize it. So let's visualize this one. So this is Q of alpha, right? And we do not like alpha, so let's say Q of x. Then two sine squared theta x squared d theta. And in order to visualize this one, what do you want to do? You want to draw a graph and shade the area, right? So you have theta axis ranges from 0 to pi over 2. And then you have a function that is here in the integrand. What is that? What is that? That function must be interpreted as a function of theta, parameterized by x. So, for example, let's see x equals 0, because that is the simplest case and we know the value, 1/2. So let's put x equals 0. What happens? This is 1 over pi, and this is 0, whatever theta we have. So this is 1. So it's a straight line. It's a constant function with respect to theta. So this is the graph of the integrand function when x equals 0, right? And then we integrate. So this is 1 over pi. So we integrate, and then what do we get? 1/2, as we expected. Now, let's increase x to, for example, 1. What happens? What happens? Theta is function. Theta is a variable, and we know 1 over. So this is theta, and we know sine squared theta from 0 to pi over 2. What it is? It looks like something like this, right? Actually, I have to say that because it's squared, Oops. Right? And then we need to put this one in the denominator. Then what happens? Something like this? Yeah, it's not exact, but anyway. So, and also you multiply x squared, right? So this curve scales up and down. So if you choose x very large, this curve goes up. If you choose x close to 0, it goes down, right? However, you need to put this in the exponent of negative something. And you know e to the negative something is monotone decreasing function, right? So what happens? It's positive, but how to say that? So this direction, x increases, right? And the opposite direction when x decreases. But now it's inside is e to the negative something. So the situation is reversed. If you increase x, the graph of the integrand goes to what? Almost flat and to the 0. And we know that q of x, when x increases, the function decreases, right? So if we plot the integrand, that is what? That is some function close to the horizontal axis, and then we integrate. However, that function is smooth, even though it may not be continuous here. Actually, it goes to 0. But anyway, so it's very smooth function, which means that you can apply numerical integration within a finite interval. This is very important. Original Q function required some cutting off. Where is this? Where is Q of x? You know, right? You know the integral. Where it is? Yeah, here you have x to infinity. So this is so-called an improper integral. Anyway, it does not have any closed form. Now what? Now what? You have a proper integral with finite length of the interval. And the function is very smooth. So numerical integration is possible. That is the first thing we can observe from just the formula. Got it? Second thing is more interesting. As I told you, in communications and signal processing, we often assume the interference or noise are well modeled by a Gaussian random variable. But we have many random variables, so sometimes we need to integrate some function that involves Q of x. So, for example, you want to find the expectation of Q of something. And instead of using this formula, right? Here you have what? You have the random variable appearing in the lower limit of the integral. What can you do? You have an alternate form. That appears inside the argument and even in the numerator of the exponent. And many of you have heard about the exponential family. By the way, what is the exponential family? Any distribution that involves exponential function in the PDF, you can say that. For example, Gaussian is in exponential family because density is what? E to the negative something squared divided by constant, right? Exponential function is, of course, a member of exponential family. What happens if x or x squared is a member of exponential family? You have what? This expectation is multiplication of this function times the density. That is also e to the something of x. And then you can group this x with that x and sometimes find very good closed form. So interestingly, expectation of q over x, expectation of q of x becomes a closed form expression with some parameter. Got it? Even though q of x must be tabulated. That appears again and again and again in digital communications. So what really happened is this. After, I remember Divsala and Simon from JPL, they were two very famous kind of couple. They were not husband and wife. They were two male researchers, friends. And they published the paper. Hey, communication people, we have found that, we have discovered, some mathematicians discovered this formula long ago. And it seems it's very useful to us. Let's use it. That was the idea of the paper. And then, of course, as a graduate student, I also was interested in that, but I was not prepared at that time to publish a paper using that result. However, there was a graduate student at University of Minnesota with his advisor, these two person, advisor and a graduate student who was a little bit older than me, kind of write more than probably 30 or 40 papers using this formula. And yeah, that happened really. Anyway, so this expression has become very famous since then. Okay. And now let's see some interesting results related to Gaussian, especially when we have x and y uncorrelated. So here goes the two-dimensional case. So far, we studied 1D case, right? Of course, in order to bound Q function that is 1D something, we kind of increased our dimension, right, into 2. Anyway, now we really consider two-dimensional case. In many cases, two-dimensional Gaussian has zero correlation and same variance. We will focus on this. Got it? Of course, if they are independent, we can always scale one of the variable to have the same variance, right? So this is not that, this is general enough. If x and y are independent Gaussian, right? Now, mean may be different. And we are interested in some integration to find the probability. First, in Cartesian coordinate, the density of x and y factors, right? So if you want to find some probability of the event x less than or equal to a, y less than or equal to b, then as I always advise you, visualize. Okay? Whenever you see some algebraic or some mathematical formula. So you want to integrate this density on this region, right? And if you are given arbitrary two-dimensional function, then this integration may be very challenging, even numerically. However, we've seen that x and y are already independent. So this integration can be actually written in this way, right? Due to the independence of x and y. And what? The first factor can be written as a cube function because this is left tail probability, which is 1 minus right tail, which means 1 minus q of something. So 1 minus q of that's something, but here we assume the 0 mean. So since this is a minus mean that is 0 divided by sigma. So we have a over sigma. And similarly, second factor can be written as 1 minus q of b divided by sigma. Got it? In polar coordinate, this is complicated, but sometimes we can use rotational symmetry. Now, let's see this one. So here, by the way, this result is to say that if we have a zero mean independent Gaussian, any rotation gives us independent zero mean Gaussian, right? That's what this shows. For every theta, the new x tilde, y tilde vector has the same density as x and y, right? That is kind of natural because the joint density is circularly symmetrical with respect to the origin. So whatever rotation we have the same thing. Now, using that one, let's think about integrating the IID Gaussian, zero mean Gaussian, on this region gamma, which has this shape. Here, two lines meet at the right angle, and from the origin, our foot has length A, and this foot has length B. Then, due to the rotational symmetry, if we rotate this area and entire thing to the previous situation, then we have what? The same result. So 1 minus q of something times 1 minus q of something. So now you understand, whenever you have independent x and y with the same variance, which means that you have rotational or circular symmetry with respect to the mean vector. Even though it is not a zero mean, you have what? You have to use that rotational symmetry to have your result in terms of Q function, right? When what? When your integration area is what? Right half plane or intersection of two half planes that meet at right angle. What if the angle is acute or obtuse? What happens? That's very challenging. Okay, that's not easy to compute. That's the problem. However, whenever you have this half plane or right angle intersection, then Q function solves your trouble. Got it? And now, okay, we've already seen that, and I already mentioned, if we find density of R and theta, when mean is zero vector, then what happens? This is the conversion formula you have to remember, or you have been remembering from your freshman calculus, that you replace x with r cosine theta, and you replace y with r sine theta, and you multiply r to get the density of r and theta. And if you plug in the density function of standard Gaussian, you eventually have this. And here you see no theta appears here. And integration of this with respect to r gives you 1 over 2 pi. So what does that mean? 1 over 2 pi is the uniform density of theta that is independent of the r random variable. So we have this joint density factors into uniform and Rayleigh. Got it? So you could use this result in your quiz. By the way, here, let's define P as R squared here. So R, the radius or distance from origin, when you have a Gaussian. So here, you plot a scatter plot. So this is X and Y. You generate X comma Y, right? And then here is X1 and Y1. Then what happens? As I told you, if you draw a line from the origin, sorry. This is theta and this is R. And for that, you can generate two IID Gaussian to find this one and that one, or this formula means you can generate independent uniform theta. That can be 0 to pi. So you choose the angle first, and you generate the distance R using Rayleigh random number generator. Then what? You have Gaussian distribution, 2D Gaussian. And you define DSP square, P square as R, sorry, P square, R square is P, sorry, R square is P. So this is root P, means R square is P. And let's find the density of P. That is very simple, as you learned in undergraduate probability and random variables. And you can find that P is what? The square distance. Square distance is an exponential random variable. That is much easier than Rayleigh, right? So you generate an exponential random variable, random number, and take the square root of it and use it as a distance from the origin. And then you generate a uniform random variable to find the angle. Then if you find a lot of points in the two-dimensional plane, then you will eventually have the scatter plot of zero mean IID Gaussian X and Y case. Got it? What else do we have? Yeah, we've done this already, right? Okay. Yeah, what if we have non-zero case in two-dimensional Gaussian? Yeah, we have non-zero X, non-zero Y, but still the density is vectors. So again, if we have the integration area that consists of that is the intersection of two half plane intersecting at the right angle, then we again use two Q functions. 1 minus Q of now, A minus mu of X divided by sigma. Here, sigma X and sigma Y are common, I assumed, right? So again, we have one-dimensional Gaussian tail and probability. And again, we have one-dimensional tail and probability. But in order to use Q function, we need to what? Standardize the value. So we subtract the mean and divide it by the standard deviation. So we plug in a unit list quantity to this argument place. Got it? What about rotation? Still, if the area is the intersection of half planes meeting at the right angle, yeah, we can do that. Okay. Probably we subtract mean and something. But anyway, we can do similarly. Got it? However, this part is very difficult and important. If we have a non-zero mean case, the conversion to polar coordinate does not give us factoring of the density of theta and density of R. And here, just a second. Yeah. So here, this is the joint density. And we see something's not correct. Here we cut off. Yeah, something like this. Yeah. Is it correct? I believe so. And you see here, this factor have R and theta at the same time. What does that mean? you cannot rewrite the joint density of an Rn theta to what? A function only of R and function only of theta. That's not possible, which means that R and theta are dependent. And that is actually very easy to expect because suppose this is the mean, right? And whenever you want to visualize a random vector, you start from a scatter plot. What happens? Then you have some points around here if variance of x and y is very small, right? What does that mean? This angle theta, right, has highest concentration of points if you have the theta close to the angle of this mean vector. If the theta deviates from that angle of mean vector, you have less, right, less points there, which means that the probability, joint probability changes, right? It's different from when the mean is 0. So there is no independence between R and theta if you have non-zero mean vector there. However, we can still compute the density function of radius. And that is painful. And here, no closed form. And people, especially mathematicians, have confronted that integration again and again and again and again and again. So they named it and also tabulated it. And here goes what? As you've seen, in some place, that is, if I remember, modify the Bessel function of the first kind, zeroth order. Yeah, zeroth order. So here goes 0. Modified Bessel function. So we use I instead of some other alphabet as J or something, and first kind. Got it? And as you've seen in the tabulation method for Q function, you do not tabulate all CCDF of Gaussian random variables. It's impossible, right? But after proper normalization, you only need to tabulate only one CCDF. Similarly, here again, this one, even though it involves sigma square and R and blah, 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 as you see here, as the argument, you somehow normalize, right, with respect to your variance. And somehow this value R, right? Then what is this chi? And here, I remember chi is the, where is chi? Yeah, chi is the square, square root of mean of x squared plus mean of y squared. And if x and y have the same unit, of course, we can add them because they have same unit squared, right? And what's the unit of this chi? That has the same unit as x and same unit as y, right? And now you take a look at the unit of the numerator. R has unit, for example, meters. Chi has unit meters. And sigma has unit meters. So you have a unit list quantity. And it seems you have correctly plugged in your argument, because usually this tabulation is for a unit list quantity. For any case, in any case you have unit, you usually normalize to some unit list quantity, right? So these are involve some strange function that is tabulated, and it looks like you can see that it's a monotone increasing function and symmetric, even symmetric function, greater than or equal to 1. And R is more strange. Why? Okay. Where is R? Yeah. This is theta, by the way. So if you rotate as this quantity, actually, they used A divided by sigma. So anyway, it's unitless. Yeah. Probably square root of chi divided by sigma square or something. I do not exactly remember that. But anyway, you can easily see that if mean is 0, the theta density is flat from 0 to 2 pi, right? If, as I shown you, if the mean becomes larger and larger relative to the variance, then every theta will be concentrated on the radian angle of the mean vector. In this case, 3 pi over 4. So you have strange density. And by the way, here goes the density of R. Yeah, that involves the Bessel function, right? Yeah. Okay, let me stop here and continue next time. Okay.